Hi guys, it's me, Deepak, and like I said the last time, I will be experimenting with a lot of my new videos, and like how I should edit the mask, and some sort of filters. How should I tell the story, or how should I make tutorials? So like this video is gonna be like me talking about OpenAI, my experience with reinforcement learning, and the project that I built. It was a very simple project, like my first time using reinforcement learning in a project, and I was like really confused, like where to begin, what to do. And like if you remember from my last Canva video, I'm not sure if any of you watched that video here or there. The video here, there I talked about how you can use. I was fairly new to OpenAI. My idea was that OpenAI would give me something like state-of-the-art algorithms, and I would be able to like use it to teach my car how to drive. But look like that's not the case. And OpenAI is basically something. OpenAI basically provides you the environments, and based on the environments, you train your model, and you see how well it does in environments. And there are also like levels that increase the difficulty. Like if you have the walking one, the cart pole, spider walking, the spider that is walking. With that in mind, I thought, yeah, this can be a new series in which I can learn reinforcement learning, make some content, and get good at it. So with that in mind, I began learning OpenAI, and the basic one, the CartPole one. Sandex has done it, but I wanted to do it with a different approach. So first, it was for me. I began with like learning how the environment works. What are the inputs, what are outputs? So if you don't know about reinforcement learning, reinforcement learning is about training the model. It has like two it all the business model has two division: model free or model based. I used a model based with policy. So the one that I'm started with, and at first it may look like very intimidating if you just open AI and see all the stuff that goes on. But no, it's very simple. There are a lot of like sites that can help you with this, and I'm gonna talk about them in this video. So like, let me just so how should I go about it? Okay, so let's just search OpenAI and OpenAI Gym. So I can start from the beginning. And uh, so as you can see, that there are a lot of environments in here, Atari games and all the stuff. And if you check the documentation, it will give you very simple this cartpool environment. It's very simple. You just have to import gym. The command is very simple. It's pip install gym. Then you have this environment. So like I want to talk about how to use cartpool, and right now we are just going to do that. So for first of all, what you need is to have gym, that is must, and I have at this point you need one. So yeah, install gym. Also I'm going to import gym first of all to start with. Then I need an environment. So for that I'll be like gym dot make, and the name of our environment is cartpool. Also you can have custom environments as well in the gym. If you ever like want to have create your own environment, like I wanna do for my snake game. Like I have created a snake game already, so I will try. But okay, so what environment.reset does is it reset the environment. You won't get like what I'm saying at this point, but let me just show you. Follow along for now, and let's see. So I will create a for loop of like so this is gonna run the statement for 1,000 iterations. So environment.render we're going to start with, which is going to show us the environment, which is our carpool environment. And then we have this environment.step function that you will see in the OpenAI site. Whenever you open it, it will show you this sample code. Environment.action space dot sample. And yeah, this is basically the code that you will see in any site, medium or any site available. We will see this as a sample code there. And if I run it, let me just go search Python 1.py. It will show you something like this. So what's happening? You are running a render function. and the step function. Render function show you this environment, and step function will move the cart pole based on the action space. So action space, if you like print action space, I mean print environment dot action space, it will give you a discrete tool. So there are two values, which is 0 and 1. As I told you, there are two options, either 0 or 1. To the, if you say 0, cart will move to the left. If you say 1, cart will move to the right. If you give the value 0, the cart pole will move, the cart will move towards left and the pole will move towards right, because of laws, because of like, hey, if you left and the pole will move toward right, like just to see. Let me just close it and I will just run it again. You can see the cart is moving toward left and pole was moving toward right. And if you give it 1, the cart will move towards right this time, and the pole will be moving towards left. No, pole is not like, we're not giving pole movement of pole as an input. Movement of pole is our output, and we want to balance it. That's the problem set. We have to balance the pole, and for that we tried an algorithm, right? So 1.pi, and you will see it move to the right, and pole will fall towards the left because of gravity or because of motion. So what this is our two inputs action space, 0 or 1. Next thing we can do is just write again environment dot action spaces dot sample. Okay, now what I need to do is I want to show you something else. What environment of step function returns, it gives us an idea about the observation, or not the idea, it gives us the observation, the state of the environment after performing that particular step. After we take an action, we get four kind of output from the four things are returned from this environment of step function. What are those functions? What are those things? Observation, reward, done, and info. Then basically tells you if it has crossed a minimum threshold, minimum threshold, which is basically if I can see it here. Okay, here you can see that condition at which the episode terminates. So our done will be false or will break when we have pole angle is more than 12 degree, car position more than that is center of the car reaches the edge of the display, so 2.4, or episode length is greater than 200 by 4 version. Okay, this for these four conditions our episode will terminate, and this is the condition that we have done. If done, the episode has finished. Also, we get observation, reward, done, and info. These four things that we get. Observation tells about cart position, cart velocity, pole angle, and pole velocity at the time. It gives us a reward. It tells us if we have terminated, if we have like crossed a threshold, like if the pole angle is greater than 12 degrees, if we have gone out of the window, things like that. And it also gives additional information. So let's start with if done. So if done, break out of the window. So we will just write break here, and if I run the command now, you can see it will break out of the loop. That's why you will mostly be using things like this. Like let's suppose I am running 5 episodes. You will be like, Deepak, what is episodes? Just follow along for now, and you will see. And I'm gonna run all these statements that I have written so far for 200 iterations. Okay, let me just move them a bit. Yeah, and every time I break out of this loop, I want to reset my environment, and there you have environment reset function. Right, now let's do it again and see. So you can see that we are resetting the environment for let's just say print reset environment, and so we can see how many times we are resetting the environment, and just cut this off. And yep, let me just run the command again. Yep, 5 times we resetted the environment. Since this time, since we're just randomly giving the inputs, we cannot like get a good reward. We have to train an algorithm for this, and that's the problem in the open. That's what the open is about. It's about giving a problem and asking you to make an algorithm that can solve the particular problem. Okay, and let's talk about observations. So what is observation, and what are rewards? So let me just talk about observations and reward. Okay, let's just print them as well so we can see them. Because observation give us about four different values in a list, and a reward giving us 1 0, obviously 1, because we are not doing anything good at this point. So observation is the 4 inputs. What are those inputs? uh, they tell us about, okay, so observation tells us about cart position, the first input that tells about the observation. The cart position, the second one talks about cart velocity, third one talks about pole angle, and the fourth one talks about pole velocity at depth. So this is what we usually give as input to a neural network or a DQN network, giving about what is the observation after the step function has been performed, after we have moved the cart, and it tells us about the pole angle and the pole velocity at depth. So this tells about the observation and reward. And yeah, so yeah, episodes are basically like every time you're done, you break out of the mid of this for loop and you start a new episode by resetting the environment. Also, like, you can be like, what does this environment or reset function does? It also gives you an idea about uh, sorry. Hey, wait a minute. Mm, let me just comment this out. We can just see what this does. It also give you the observation space as well. This function also gives it. So if you want to like check the difference between two if you're no, like not like that. I was thinking about something else, but yeah, this will give you an idea about observation space when you reset the function. So this also gives you the observation space. Step function also returns the observation space. Also, I have already like implemented the what do you say, the DQN network using TF agent. So let's talk about what I have done in that. So based on these observations, so like what reinforcement tells us? It tells us reinforcement begin with us having no knowledge about what to do in a particular environment. We just go and explore. If we do something good, that means it's something that we should have done, something that is an optimum action that is considered by the environment. We give a positive reward, and if something that we do, like suppose we go out of this, go out of the like our window, and episode terminates. That means it should give a negative reward. If our pole is greater than 12 degrees, that means it's a negative reward. But if it keep balancing it, we should give it a positive reward. So like if it's not terminating, then we should keep giving it positive reward, small values, not very big one. And if we do something bad, then we should give it negative reward. It's very intuitive if you think about it. My with what I was doing was training a model. It has like environment observation. It can observe the environment, and based on the observation it will take the actions, and I have to train my policies up to the point so that it can take the desired outputs. Like if you check one of the best algorithms simulated for this to get the maximum reward, mostly the PID controller. Like I find myself so stupid. Like I also use the PID controller in my self-driving car part 2, if you know, like share here, where I use it to drive my car, and be able to like not like jump into buildings or cars, other cars, not other cars, just buildings. I was just getting the waypoints. So using PID controller also you can actually do it. So this like gives you something like you should not be so much focused on like using reinforcement learning that you ignore all the other options. Environment is there. It has like they think of it as a problem that you have to solve using anything in your arsenal. It's not always about okay, so someone is doing with this approach, so we should also do it with the reinforcement learning. You can do it with any type of algorithm that you want, or you can use the PID control as well, or you can use a deep convolution neural network. Like no one will be judging you. OpenAI is just like giving you the environments for you to train and see how good your algorithm does. So if you're just using a simple PID controller, that's actually saving time for training a network and all the other stuff, or the complex computation that to do. So my point being, don't like just fix yourself too much on the problem. Sometimes you already have the solution, or like that. I first begin with like when I was like looking for how to solve the problem. I looked a lot of like a lot of how should I say this, built-in reinforcement learning algorithms, and one of the I think Stack Overflow also talked about baselines, and like talk about it has like one of the best. So you can say as a set of high quality implementation of reinforcement learning algorithms, they're going to make it easier for research communities to applicate, redefine, and identify new and create good baseline to build research on top of DQN network. But it is very hard to install on like Windows, where I am running or I'm doing the whole project. It's not working on Windows, and on Linux also it's showing me some errors. So I wasn't able to work with baselines to use predefined reinforcement learning algorithms. But then TensorFlow come into picture. TensorFlow has like if I can show you TensorFlow TF agents. TensorFlow DQN another way TensorFlow agents. This actually solves the issue. This actually gave me the whole solution on how to like able to be build a problem, how to actually use a deep Q network. Like I knew nothing before this, so like everyone has to start somewhere. Like I started with the copying tech with Tim code for the Flappy Bird, and after that I created Snake game and the Chrome dinosaur game. I never completed it, but almost did it. So yeah, it counts. So yeah, I had to start somewhere with this thing as well. So like yeah, don't be like yeah, Deepak, you're just copying the code again. But yeah, everyone has to start somewhere, right? So this site actually explained pretty good. That's why I'm making a tutorial about how to like use DQ network. It has to like import all these libraries. You don't need few of them like image.io. I'm not using this basic. Not using all of them like this Pi virtual display. You don't need it. If you are working on Windows, you need it. If you are in, I think in Linux, it was giving me an error in Windows, and when I checked it out, it's not suitable for Windows. The guy that said it, so I just removed it, and it was working fine for me. Because you have to this is for rendering the episodes, and you can render the episodes easily on Windows. You don't need it. After that, you have these parameters about initialization step, collection, replay buffer. So buffer is needed for collecting the data and then training our policy. I'm not sure if I talked about policies that much, but I will in some other video when I have a bit more information. A bit when I am a bit more confident. I mean to say, I am not at this point. Here I'm using this CartPole-v0 and I'm using Scoot to load the environment from OpenAI. It also has some other options like Atari and game controller. I'm like really excited to use one of these algorithms in Breakout. If you know, I failed last time, and my friend told me A3C is pretty good for Breakout. So I like really want to check out A3C at this point. But yeah. So after that we have this and then render the episode. You can render the episode in Windows just like in memo.render. It works. Then the algorithm used to solve our algorithms. So there are like few algorithms. So we are using DQ network. And I think you should go and check out what is Q-learning. It's pretty simple. You just go and see how it calculates state action values and all the other stuff. It's pretty easy. And also, like, check out Wellman-Ford equation, how it works. It will give you some insight on how this whole thing works. So at first we have like two we are creating two layers of 150 nodes. Define a helper function to create a dense layer. So we are creating this helper function. We have set the initializer, like what values to initialize with using initial variance scale and using truncated normal distribution and scale 2.0. Then I'm creating this calling this function where I'm passing the unit. So first I'm passing 100, then I'm passing 50, and getting this this whole these two layers. After that we need output layer, which is this Q value layer, where I have like this again a dense layer with no activation function and and an initializer with range between 0.03 and 0.03, negative 0.03 0.03, and with base initializer can initialize the constant minus 0.2. Pretty simple one that I add this two layer, and this is my Q network. So this is what I needed. Then I have this agent where I pass in train environment, the action space. So time step space I didn't talk about. Yeah, here it is. So this gives you idea about the shape, the type, like name observation, minimum values, and the maximum values about the observation. Also for time step spec, also give you the information about the rewards. You can check the shape, float, name, reward. So reward is basically the one. No, reward is basically simple float integer float. It's not an array. It's basically just a float. Float 32. I don't know why I'm keep saying integer again and again. After that, you create this network. Then you pass train environment or time step spec, then action spec. Action spec also I think returns uh, like this integer action and action minimum 0, maximum 1, 0, 1, like left or right, move the cart pole in that case. So you have to pass the observation rewards here action spec, then that Q network, then optimizer, which is an item optimizer, will linearly equal to 1 e minus 6, 6 and TDI loss function, common element dot by square loss error, and time step counter, time step counter. All of these are defined in the hyperparameter here, right? Not sure this one. Yeah, here's the learning rate. It's sorry, minus 3. And then we have two policies like we talk about. Policy define the way an agent act. So our main purpose is to train our policy so that it will give us the desired outputs. So the desired output is keeping the pole balance up over the cart. The policy turns an action for each time step observation. And agent contains two policies. Agent policy is the main policy that is used for evaluation and deployment, and second is for collection data for data collection. And this is how we call these two policies. Policy and policies. After that, we can also like create a policy using TensorFlow agent of policy random. Here, this one, random policy. We will see this in action. Random policy doesn't do that well, and obviously, I mean, so we have like this example random reset. This is nothing. After that, this is how we like compute the reward. So we have the environment reset, episode return 0. Then you have this time step dot is last, like until episode is broken or terminated. Action step, we take the action, we pass the time step. Time step is this environment reset or environment of step always return a time steps, or you can also say like time step spec, anything that you want to say. Then we number of step, episode returns, total episode, then we compute the reports. This is how we collect information about our, this is how we use data collection. So transfer.uniform.replay buffer. We imported this up in our library. After that we have a general data spec, batch size, and replay buffer at max length. After like so here you collect the data. and this is just a buffer that you've created. Here in this buffer we are going to like add everything that you want. Here you see us passing the buffer here. So first of all, like this is where we call collect data. Here we run a for loop for each step. So initially we have initial collect step, like remember we have like 100 of them. So for in range, so we are going to run this, call this function 100 times, environment.policy.buffer. And our environment is basically our train environment. We have created two, train environment and evaluation environment. And we have this policy which is our random policy and buffer. Random policy is basically used for data aggregation at this point. So we have a time step which is a return from this current time step. Then we take then we pass this to our posted action step, and next time step environment or step action, and then we store it into then we call this trajectory function to store time step, action step, and the next time step. So between all of this, what I have aspired so far. So this is what we use for. Here we train the, before that here the buffer, and we've created a data set, replay the buffer as data set. So assemble batch size, prefetch 3. Simple. After that, agent.train step.assign 0, then compute the reward. Initially, we evaluate the performance before training the reward. For in range, complete collect a few steps using collect policy and save to the replay buffer. Collect train data, if you remember. We used call this function for random policy with passing random policy. Here we are passing collect policy, a replay buffer and collection step iteration. Collect few steps using collect policy, and sample a batch from data from the buffer and update the agent networks. Unused next iterator train loss agent or train experience dot loss, and after that step agent or train step content dot compare. After that, here it is. Here you train your policy, and here you can actually check how well it does after training. And here you also check out how random one done. Random one is not doing that well if you see, but the one that you train does pretty well for 5 episodes. I mean, you're just calling it for 5 episodes here. So yeah, this is basically how they taught you about DQ network. I mean, they did a pretty good job. I will just see the link. You want to check them out. Yeah, right. But also something good that happened this year. This month, I got a mail from Openai. I just like mail them about asking permission for their private beta API, and they gave it to me. So yeah, next video is gonna be pretty awesome. I'm gonna, like, if you remember, I made a Discord bot, which was pretty bad. I just have to hard code every output. Like, what if I can export GPT-3 code and use it to have smart replies for my for people. Like, people can communicate with the with my chatbot and have some meaningful conversation. Like, I have like almost an hour conversation with GPT-3, and like I have some initial views. It's pretty good. First of all, you can have conversation about anything, and it will keep talking about it. It will not give its personal opinion on anything, which I find like really funny. Like, you can ask him about anything, but do you like, what are your preferences? It is not going to say anything. So yeah, it's pretty. It's it is trained very well at that task. Also, like, if you keep talking about one thing for a very long time and then you suddenly to the conversation, it will get confused. It will stutter. It will keep repeating the last line again and again. That is something that is there. But it will like to get temperature a bit, and then it will, yeah, it will then work, and it will be able to jump back. So yeah, there is this toggle that you have to you can just tweak a bit. Also, yeah, I mean, it is pretty fun, and it's like really powerful thing that That's why I think they're not giving it to everyone, because it can be misused. Like I read some of the things, like how it can actually, if you with enough information, it can talk about, or it can act like that person. Like if you give it a lot of information about how they do it or how they talk, it will be able to generate something that they might say. They have not, but they can say, like if you ask them about this particular question. So yeah, this is something that is yeah, very powerful and can be exploited. Also, I want to check out if I can use this to like generate code. I have seen one video where that guy like generate code by training it on a lot of GitHub code. That is something that I really want to try. And I think I should like stop now. And yeah, thanks for watching. Bye. Yeah, subscribe also if you like the video.